right. Okay, we are live. Hello, everyone. Welcome, class. Feel free to ask questions in the chat if you would like. There does appear to be about an 8-second latency, so like, if you ask a question, it might take me a minute to get there. But hello, welcome. Today we are doing an introduction lecture for the basics of statistics in psychology. This is going to be at an undergraduate level, so I'm going to keep things pretty simple. And hopefully you at least find it not super painful. That's the ultimate goal. Okay, so yay statistics. First things first, let's go with that. First off, I wanted to introduce myself a little bit. I'm not sure if I've ever actually done that in any of my videos, so whoop, I figured it was probably time. I think the PowerPoint's gonna go crazy for about a second. Okay, so who am I? Well, first of all, my pronouns are they, them, theirs. I have a PhD from Point Pleasant University in social psychology. I'm Mylan Aikman, by the way. That's my name. Looks like I left that off the slides outside of, the very first slide. My research, I primarily do research on anime, at least as far as this channel is concerned. We're not going to talk about my real research. And as for today's agenda, first, I'm going to try and convince you that you should care about statistics. Then I'm going to talk a bit about how this class is going to work. I'm going to go over some basic things. And that's it. Pretty much. We're taking it pretty easy today. I might move myself a little bit so it's easier to see things. Get real tiny down in the corner here. Hi! Hi. Oh. Okay, so I actually do teach this class as part of my job, and I figured I would share some data from some previous classes with you. See, a lot of people who come into my class are really nervous about statistics, which, is fair. It's a pretty intimidating topic, at least it was for me. So I want to show you a quick little survey. Every semester, I ask my students how nervous they are about math and how nervous they are about taking a stats class. You can see on the x-axis here, we have how nervous they are about math, with 1 being not nervous at all and 5 being very nervous. And on the y-axis, we have being nervous about statistics. And there, a 1 is not nervous at all, and a 5 is being very nervous. So, here we have a correlation. You can see that the more nervous about math my students were, the more nervous about the stats class they were. And, fair. It's scary, isn't it? I was very scared when I was an undergrad to take stats because, frankly, I was bad at math. I'm still bad at math. I'm very bad at math. But just to give you a preview of something that we'll be talking about in some weeks, this is a correlation of 0.59. That's about a moderate to strong correlation. So these two things are fairly related. If you're nervous about math, you're probably also nervous about stats. This is p is less than 0.05. What that means is that this is probably a real correlation. It probably reflects some real relationship between anxiety about math and anxiety about statistics. Probably. And the sample size is 32, so this represents data from 32 different students. So if you were nervous about it, I wanted to show you some memes. Statistics is not math. And this is a common source of amusement among mathematicians and statisticians. Here are some real memes I found online. I did not make these, so hopefully maybe that lends me some credibility. Her, I'm a stats major. Me, trying to think of something to impress her. Yeah, I'm bad at math too. Me talking about statistics, me talking about any other math. This is me. This is absolutely the type of person that I am. And here's statisticians talking to mathematicians, statisticians talking to scientists. This is very much the vibes that are happening here. This is very much what it's like. So if you are nervous about statistics because you're bad at math, don't be. Like I said, I am bad at math, but I like to think that I'm pretty good at statistics. So don't freak out, it'll all be fine. I will do my best to make it as painless as possible. So who cares about stats? And I've added some anime images in here, because, that's kind of my thing. Who cares about stats? Well, first of all, psychologists care about stats, or else why the heck would a psychology YouTube video be making a video about statistics? Scientists in general care about statistics. Researchers in general, a lot of research is based on statistics. Who else cares about stats? Well, athletes and the people who are in charge of athletic teams. Statistics are used in sports a lot, and a lot of money is often on the line when they're using these things. You might be looking at team statistics, individual statistics. There's a whole field of statistics called sabermetrics, which is statistics about sports. I'm not very informed about sports, so unfortunately I can't tell you more about that. But if this helps, if you're interested in why you should care about statistics, even if you don't care about sports, let me tell you a story. Every March in America, there's this thing called March Madness. It's a bracket of college basketball teams. I think that shows you how much I actually know about sports. I don't even know which sport this is. And a lot of people like to predict who's going to win each bracket, and then you can score your brackets and like compete with your friends to see who has the best predictions. And I clearly know nothing about college level basketball. I think that's what March Madness is. But I have won or tied for the best bracket 2 years in a row by using my knowledge of statistics. We don't actually win anything in my family. I just get bragging rights. But it is nice to get bragging rights over my family members who actually really care about this stuff. Who also cares about stats? Well, people who care way too much about power scaling. You will see this a lot in anime. People argue about statistics. They're usually using pretty basic statistics to argue about this, but it plays into this too. I'm sorry if you're not into power scaling. But if you are, maybe this series of lectures will. Who cares about stats also? Well, streaming services certainly care about statistics. Anime production companies, manga publishers, game developers, all of these companies care a lot about statistics. They determine what type of manga and anime are come out. They determine whether a series will keep running, whether it gets extra merchandise, whether it gets an anime adaptation. On the right, we have a manga called Ayashimon, which was by one of my favorite manga authors, and unfortunately, the statistics it was getting in terms of weren't great, so it got canceled. I, too, am a victim of statistics, and this manga was as well. Very sad. Alright, so syllabus. Let's take a look at the syllabus. Slides. I'm planning to upload all the slides for this as PDFs to a Google Drive folder that will be linked in the description of the VOD when I put that up. That's the plan. That way you can review the slides as well if you want to do that without looking through the entire video. Class will be streamed live, so I plan to do all of these as live streams, and recording will be available for people who can't make for class time and for review. So, VODs. There will be VODs. Practice. I am planning to do some practice problems with all y'all. I'm looking to do it mostly with real data from anime-adjacent databases. I have some old data from My Anime List, which is a website that a lot of people use to track their anime viewership, like which shows have they watched, how much have they watched, you can star ratings. I'd like to use that data. I have data from some like characters in mobile games. I've got Fate Grand Order data sets and things like that. So I really would like to use some real data from things that, you know, anime fans might like to make it a little more interesting to you. As far as the format is concerned, I will usually start the class by reviewing concepts from the class before. I am happy to answer any questions that you put in the chat, so long as they're, you know, appropriate questions. I will do my best to answer statistic questions, and I can be pretty reasonably sure that I'll have a decent answer for you, or at least be able to point you in the right direction. If it's not related to statistics, I cannot promise I'll have a good answer for you, but I'll try. But yeah, if you have a question, other people in the chat do too. This is totally anonymous. You're just using your YouTube username, and I'm not judging you. I'm not grading you. This is an extracurricular class. And I love answering questions, so please don't hesitate to do that. If you are watching the VOD, feel free to drop them in the comments section. It might take me, well, of course it will take me longer to get to those. I will do my best. We'll go over the math together, so when we are doing math, we will go over the math together. I will be doing it with you. I'm going to be writing it down manually. I still need to figure out quite how I'm going to do that. But that way you can watch me work through a problem, and maybe if we get enough people live in the chat, I might ask you to help me along with the problem. So what would we do next year? Like, of course I know what we'd do next year, but you know, I'm going to try and make it kind of interactive if I can. So that's kind of the plan. Now, the time has come. We are going to learn. We're going to get to the actual material now. Everything up until this point has more been like, you know, setting the scene, what to expect, that kind of thing, and also trying to get you to care about stats. So, key definitions that you will be haunted by for the rest of this series of lectures. By the way, you'll notice in the upper right-hand corner of this slide, there's a stamp that says important on it. That stamp indicates that this is a slide that's going to, like, the information on here is going to keep coming back over and over and over and over throughout the entire series of lectures. You will not be able to escape this information, so if you're taking notes or something like that, you might want to come back to it, or if you're zoning out, I totally get it. I get it's normal to, you know, zone out during lectures, even if they have a cute anime character saying them. These are slides that you might want to zone back in for, because if you... Yeah. Anyway, first big definition, population. Population, in statistics terms, is all of the individuals in a given group, or all the items in whatever collection that we're looking at. So, for example, a population of anime watchers would be every single human being, or dog, or whoever's looking at the screen. Every single living creature that has ever watched an episode of anime. And these are defined by numbers called parameters. So if I wanted to know, say, the average number of anime watchers watch, or like, say, the average number of episodes they watch, their average rating that they would give an anime, I would need to get... That average would be called a parameter, and to get it, I would need every single individual who's ever watched anime ever. Depending on how strict you are, this might be living or dead. If you're not super strict, it might be just among. Then there's samples, and we work with samples a heck of a lot more than we work with populations. Samples are just a selection of individuals who are usually, well, hopefully, randomly selected from the population. So they're a small chunk of the population. So, for example, let's say I got 50 people who've watched an episode of anime instead of every single living creature that's ever watched an episode of anime. And if I wanted to get, say, their average rating of an episode of an anime, or the average number of anime my sample watches in a season, that number would be called a statistic. So we call this statistic because we're often working with samples. We're using, like, the average number of people in this sample who did this, or, sorry, the average in this sample, the average rating in this sample, the average number of episodes watched in this sample, that kind of thing. So populations, parameters, both start with a P. Samples are described by numbers called statistics. Start with an S. I find that helps. Now finally, there's something we call sampling error, and this is a huge, major concept that will keep haunting you throughout this entire, you know, series of lectures. Populations, we're going to touch on them for the first few weeks of this. Samples we'll be dealing with for pretty much the rest of it after we get through populations. Sampling error there is always going to be there. Always going to be there, no matter what. It is a major... It's the whole reason statistics are necessary in the first place. So what is sampling error? Sampling error is the difference between a sample statistic and the population parameter. So let's say I want to know the average number of episodes of anime a person will watch in their lifetime. I get a sample of people who are currently in the room, and I get their average, and then I somehow get the average of the population. So I know the true average of all people who've ever watched anime, the true average of the number of episodes they've watched, and then I get the average number of episodes watched for my sample. Sampling error is the difference between those two. See, no sample of people is ever going to be exactly like the population. A group of 50 anime watchers cannot possibly perfectly represent every single person who's ever watched an episode of anime, right? Like, you can't just get a small number of people and assume they're exactly representative and exactly the same as every person who belongs to that same group. So the average number of episodes watched you get from your sample is going to be different from the average number of episodes watched in the population. That's just how this works. And the difference between those two numbers is sampling error. The difference between your sample and the population that you're trying to study using that sample. And don't worry, we'll talk about this concept a lot more and in a lot more detail later on, because it is a major, major, major thing. The whole field of statistics. Now, statistics, generally, there are several branches of statistics. For the purposes of this class, we're just going to divide it into two branches, or two different types of statistics. The first type are descriptive statistics, which we're going to be talking about this week and next week. Descriptive statistics are just used to summarize data. They're not trying to draw any conclusions or answer any questions from the data. They're just summarizing a bunch of numbers. So rather than looking at, a spreadsheet filled with numbers and stuff everywhere, it's a summary. It's saying this is the average of all these things, or this is how much these things tend to differ from one another. But it's not trying to tell you every single thing, and it's not trying to help you learn, like, if I do this, what happens? It's literally just a summary. It's the cliff notes of a data set. Then the other type of statistics are inferential statistics, and this is what we'll be getting on from like week 3 of these lectures onwards. These are techniques that we use to make generalizations about samples and apply them to populations. So to put that in other words, all that's saying is inferential statistics are statistics that we use to answer questions. If you've heard of, experimental design, we have a treatment group and a control group. Are they different? Did this medication actually make a change in symptoms? Did this intervention change this or this or that? That is the kind of stuff that you are doing in inferential statistics. It exists to answer a question. Usually, are these two things different or are these two things related? Something along those lines. So descriptive statistics is just summarizing stuff. Inferential statistics is trying to create new information. Not just a summary, it's trying to, create some new info. All right, more vocabulary. Research terms. First off, variable. A variable is some measurable thing that might be expected to vary over time or between individuals, which is, I know that's really vague, but that's because a lot of different things can be variables. So for example, the number of hours of anime somebody has watched would be a variable. Some people watch more, some people watch less, some people watch none, some people watch almost all of it, which is wild. And this can be things like height, this can be things like weight, this can be things like power level, if a character's in their training arc or whatever. All these things are things that can change over time or might differ between people. Most things in the world are variable if you go on a big enough scale. A constant is a character is something that doesn't change. It's the same across all people. It's the same across all of time. For example, the number of letters in the word anime is a constant. It's always gonna be 1, 2, 3, 4, 5 letters, at least, when we're talking English and things, the way we spell it out in English. Unless some major thing happens in the future and then change how they spell it. But, that will be a constant. That is something that does not change. Everybody, theoretically, should spell it the same way, as that is the so-called correct spelling. And it should keep being spelled that way for pretty much ever. Constants, honestly, are really rare. I struggle a lot to come up with examples of constants, because given enough time, it's possible that the way that we spell anime will change. If you are using a different alphabet, the way that you spell it changes. It's difficult for me to come up with a true constant. I once was like, oh, well, the number of planets in a solar system, or in our solar system. But no. They took my precious Pluto. Anyway. I guess you could argue that Pluto was never a planet by that definition. Anyway, variables are something that differs between people or over time or both. Constants is a number that will always stay the same. Mostly we are going to be dealing with variables. We will rarely deal with constants. All right, types of variables. Let's talk types. First off, discrete variables. These are variables that are indivisible categories. The number of views on this VOD, or the number of people watching this stream. You cannot split people into fractions. You are not half of a person or a quarter of a person or whatever. Everybody is a whole person. When another person joins the stream, that number goes up by exactly 1 unit. When one person leaves the stream, that number goes down by exactly 1 unit. There are no fractions here, there's no decimal places. That's a discrete variable. These categories cannot be divided. Then you have continuous variables. These are variables that can be divided. They can have decimal places. So this has an infinite number of possible ratings. Like, possible values. Distance can be measured in feet, but that can also be split up into centimeters, or millimeters, or inches, or half inches, or meters, or kilometers, or miles, and you can slice those up further. Height is the same way. Rating of an anime, you can rate an anime something like 2.5 star. I guess it depends on what system you're using, but you don't have to stick to full stars, right? You can use fractions of stars. Continuous variables can have decimals, discrete variables can't. It's kind of the short version of it. Now, scales of measurement. So variables, so these things that differ between people or between individuals and across time, they're either discrete or they're continuous. You can either divide them further or you can't. They're either full numbers or they can be split into smaller numbers. And then you have scales. Every variable has a scale of measurement. Sometimes the same variable... I'm getting ahead of myself. Let's talk about the scales of measurement. First things off, some variables are on a scale called the nominal scale. Nominal is in name. Nominal scale variables are variables that are categorical. These are just general categories, and there's no inherent order to them. Could you put them in an order? Sure, but there's no reason they have to be in that order. So for example, the genre of anime that you're watching, those are categories, like slice of life, shonen, drama, isekai, all these things, they're categories, but there's no reason we have to sort them in any particular order. We could put them in alphabetical order, we could put them in order of which one has the most anime in it, which one makes the most money, but there's no inherent order right in there. Some genres are not inherently more or less than other genres. That's a nominal variable. It's categories, and they don't have to be in any particular order. You can put them in any order, and that's equally valid, more or less. Then we have ordinal variables. Ordinal variables, as you can kind of guess from the name, these have an order. They're still categorical data, so they still have categories. They're often discrete, so like you can't divide them into decimal places, but there's some sort of logical order to them. Some things are higher than others, some things are lower than others, or some things are more or less than others. So if you're seeing a ranking of, say, the top 10 anime fights, like a Watch Mojo video or something like that, this would be an ordinal variable. Some are higher than others, some are lower than others on this list. Star ratings, so 5 stars, 4 stars, 3 stars, this is also an ordinal variable. 5 stars is more than 3 stars, 3 stars is more than 2 stars, but you can't say the difference in quality between a 1 and a 2-star anime is the same as the difference in quality as a 2 and a 3. You don't really know how big the gap between the units are, and it's not necessarily consistent. So you can think of this like place in a race. The person who finished in first place might only be seconds ahead of the person in second, and the person in second might be minutes ahead of this person in third. The distance between the units isn't necessarily the same, but there is a clear order to them. Things like rank in the military, the difference in power between ranks isn't necessarily even as you keep going up the pecking order, but there is a clear order of this person has more power than this person. Birth order in siblings is also an ordinal variable. There's clearly an oldest sibling and a youngest sibling, but let's say the difference between the youngest and the middle sibling is only a year, and the difference between the middle sibling and the eldest sibling is something like 3 years. There's a clear order to it, but the units aren't the same size. You're not going up by the same amount or down by the same amount as you move between units. That's an ordinal scale. In psychology, we use ordinal scales a lot. Anything that's like, how do you feel about this on a scale of 1 to 10? How happy are you on a scale of 1 to 10? How often during a week do you feel like you're not getting enough sleep? 0 no days a week, 1 some days a week, 2 most days a week, 3 all days a week. That's an ordinal scale. Then we have interval scales. Interval scales have the order, so there is an order. Some things are greater than other things. Some things are higher or lower than other things. And the units are the same size. So in this case, going up by 1 unit is 1 unit is 1 unit. You keep going up. So Celsius and Fahrenheit, a change in 1 degree is always a change in 1 degree, no matter if you're going from 21 to 22 degrees or from 0 to 1 degree. That's still just 1 degree, and that degree is always the same amount of change. Now, Interval variables are a little weird. They don't have something that's called a natural zero. They have something called they have an arbitrary zero. So a zero on that scale does not mean zero of the thing that you're measuring. So for example, temperature when measured in Celsius and Fahrenheit is an interval variable. 0 degrees Celsius and 0 degrees Fahrenheit do not mean there's no temperature. They just mean it's cold. And yes, 0 degrees Celsius is the freezing point of water, but there's no reason they had to make it water specifically. They could have made it the freezing point of Diet Pepsi or whatever, right? 0 point is arbitrary. It doesn't mean that the thing that you're measuring is absent. That's an interval variable. And finally, we have ratio variables. This is a case where there is a specific order. Some things are higher than other things. Some things are lower, or some things are more or less than others. The intervals are constant, so all the units are the same size. If you go up by 1, you are always going up by 1. And the scale has an absolute 0 point. If you have a 0 on this scale, that means whatever you're measuring is not there. There's 0 of whatever you're measuring. So for example, the number of episodes in an anime. 1 episode is 1 episode is 1 episode. You always go up by 1 or down by 1. There is a 0 point. You could have something that just straight up does not have an anime, and therefore it has, 0 episodes. There is a true 0 point, and there is an order. Some shows, like One Piece, have more episodes than other shows, like Morio no Hako or whatever. Distance is also a ratio variable. You can have 0 distance. 2 things can be touching or what have you, or you can have a great distance. An inch is an inch or a foot is a foot, no matter how far you're going or how short the distance is. And there is all the units are the same size. There is an order. Some distances are bigger than others, all that. And DPI of an image, so the number of dots per inch or the number of pixels of an image. You could have an image with 0 pixels. I guess the image at that point wouldn't exist, but you can measure an image in pixels and get 0 for an image that isn't there. More pixels. Each pixel is adding exactly 1 pixel. All pixels are the same size. Goes up, goes down. There you go. These are our 4 scales of measurement. Nominal, categories no order. Ordinal, categories with an order, but the units aren't always the same size. Interval, there is an order. The units are always the same size, but 0 doesn't mean there's 0 of whatever you're measuring. And ratio, there is an order, units are all the same size, and a 0 does mean there's 0 of the thing that you're measuring. Ta-da! So, you don't have to, I recognize there's relatively few people currently watching. If you're not comfortable answering these questions in the chat, you don't have to. You can just think to yourself or what have you. But I'm going to go through some examples. We're going to look at this and say, okay, what type of scale of measurement is this? Is it nominal, ordinal, or interval ratio? Or interval or ratio? First off, how many angry comments Dr. A gets for saying that JoJo's Bizarre Adventure is overrated? Nominal, ordinal, or interval or ratio? Scary. Scary. I'll give you a minute to think about that. Take a poll. Is that a thing I can do? One day I'll figure out. Oh, I can! Alright, yes! Is this nominal, ordinal, interval, or ratio? There we go! Oh, sorry for the noise. So let's see, the number of angry comments I might get. It's a number. Can it be 0? It can. Yeah, you're right. Yeah, it can be 0. Theoretically, I could get 0 angry comments, which would be nice. With my audience size, I might actually be able to pull that off. Gonna give it another little bit. Oh, there's a vote. We have a vote. Okay. Ending poll now. You are correct! This is a ratio variable. Oop. This is a ratio variable. It is possible for me to get 0. One angry comment is another comment. No, you're right. You're right. You're totally right. It's ratio. So, yeah. One angry comment's increase is another angry comment's increase. It's each angry comment is just a comment. It's, you know, 1 increase, 2 increase, 3 increase. You could theoretically get 0 angry comments. So the units are the same size. There is a rational 0 point, and some numbers are higher and therefore more than other numbers. Exactly correct. Great job. All right, next example. I'm gonna mess with you a little bit. I'm not actually gonna mess with you a little bit. I guess I kind of am. Depends how, like, terminally anime you are. This might trip you up. What scale of measurement are the letters F, M, A, and B? Yes, exactly. Yeah, you can do math to it. You can multiply and divide, all that stuff. All right. So these letters are... Oh no, forgot my keyboard's kind of broken. Nominal. So please excuse me if I misspell something. It's because my keyboard isn't working correctly. Ordinal, or interval, or ratio. There we go. The letters F, M, A, and oh. Give it a minute. A little bit. I do see one vote in there, but I want to make sure that everybody who wants to has a chance to say something. Or to, you know, vote. Also gives me a chance to take a sip of water. Okay. Gonna end that poll. Correct! This is nominal! Good job! You did not get fooled by me invoking Full Metal Alchemist Brotherhood. There's no reason those letters have to be in that particular order. Letters are categories. They don't necessarily have any, you know, one letter is not more than any other letter. Sure, there's alphabetical order, but you could order them in many other ways as well. You could order them by what order they are in any given word. You can order them by how many times they're used in a dictionary, whatever. There's no specific order to them, right? They're a nominal variable. Letters are categories that can be put in any order you want, and there you go. Great job. Okay, I got another one. Oh, no, I don't. Let's see. I was gonna ask if you can stump me. There are definitely things in here that you can stump me with where, like, sometimes it depends on how you measure it. So, like, let's say you're measuring stress. Depending on how you measure stress, you might get very different scales of measurement. So, for example, if I measure stress in, say, the cortisol concentration in your blood or whatever, that might be a ratio variable, but if I measure your stress on a scale of 1 to 7, from 1 being not stressed at all to 7 being extremely stressed out, that would be an ordinal variable. So if you want to try and stump me, it's okay if you don't want to, but if you do want to try and stump me or give me something to chew on, I will do my best. Take another sip of water. Oh no, I'm out. That's okay. This will carry me. Right? Or I can just quiz you on some more. Color is another weird one, actually. Because color is like... Color, depending on how you think about it, yeah, it can be nominal. Colors can be nominal. They don't have to have a particular order. But say if you're using things like RGB values, then you might be getting somewhere completely different. You might start moving into the realm of, say, the amount of red in this particular color would be a ratio scale. It gets wild. Ooh, as for how language influences how... Yeah, the Sapir-Whorf hypothesis! There's been some interesting work on that lately. I think it might be struggling to replicate, actually. I'll have to look into that more. But yes, that is such an interesting thing. I think it's really cool. I need to I need to look into that more. Yes, yes. But you're right, yeah, that would also make it even more complicated, because then maybe people perceive color differently depending on the culture that they're in as well. Alright, sorry. I gotta stop getting distracted. Let's go on to the next one. Yeah, to how language influences how we name the study of language is incredible. Like, both the psychology of it and then just linguistics as an entire field is super cool. Like, I do text analysis, but, like, the study of language in general is not something I know much about, but what I do know about it seems really, really neat. I need to learn more. Maybe we can, like, read an article together or something. Alright, okay. So, more definitions now. We're setting down sort of the basics. So there's a couple of methods that you can use, or types of statistics. The first sort of method that you can do statistics with is the correlational method, and you'll notice that little important thing in the upper right-hand corner again, just to tell you, hey, this is going to come back a lot. Correlational method looks at the relationship between variables, two or more variables. How do these things go together? This can be things like height and weight. How height and weight do tend to be related. Number of manga chapters and number of anime episodes. Longer manga do tend to have longer anime, but that's not a perfect relationship, right? Sometimes short manga get like huge. I guess it would be more accurate to say maybe you might have a long anime that is translated into like they might have like a manga anthology that's pretty short, or you might have a very, very long manga that gets a very short anime adaptation because it's not well received, but typically the longer the manga, the longer the anime, right? Those two things do tend to be related. The size of a figurine and the price. I collect a lot of anime figurines, so I know that the bigger figurines are more expensive. Is it a perfect relationship? Absolutely not. But those two things are related. Bigger tends to be more expensive because it uses more materials. Rainfall and mood. When it rains out, you might be sad. I know that there are a lot of people who the amount of sunlight there is outside, that will negatively affect their mood if there's not a lot of sun, if it's cloudy out. So these two things are related. Is it a perfect relationship? No, but they're related. There is a correlation. Now, of course, I have to say, the typical disclaimer. Correlation is not necessarily causation. Just because two things are related doesn't mean one of them caused the other. But, if one thing causes another, they will be correlated. Yeah, the number of people buying ice cream and pool drownings. Yes, those two things are correlated. But buying ice cream does not affect your ability to swim. And swimming does not make you buy ice cream itself. Those two things do tend to hang together, but one of them isn't causing the other one. For examples of these correlations where one is obviously not causing... This has to do with the values of P and R, right? Yes! Yes, we'll get to that much later in the series of lectures, but R is a correlation coefficient. It's a number that tries to describe how related two things are. The bigger R is, the more related they are. The smaller R is, the less related they are. Absolutely. And then P tells us, essentially, do we think that this is a real relationship, or is it a fluke based on our data? Yes. Absolutely. Good memory. All right. So let's look at the spurious correlation. Spurious correlation, by the way, is just a correlation where two things are related, but it probably doesn't mean anything. This graph is a bit confusing. It's from the Church of the Flying Spaghetti Monster. Let's see if I can... It's from the Church of the Flying Spaghetti Monster. On the x-axis is the number of pirates. Is the scale at the bottom ordinal since it's not linearly arranged? Yes! This would be an ordinal scale. I guess if you wanted to get technical, it might be on some sort of scale like logarithmic or something, but yes, it's ordinal. The size of the units aren't the same. Very good! Great job! Yes. But yeah, it's also organized weird because the higher numbers are towards the left and the lower numbers are to the right. This is a very... I wouldn't say this is a very informative graph, but it's a funny graph, and I don't think it's supposed to be super informative, so that's okay. So the number of pirates is related to the global temperature. As global temperature has gone up, the number of pirates has gone down. That's a relationship, but it's probably not, because one of those things is causing the other. Here's another one. Eating margarine makes you get divorced. No, it doesn't. This is another spurious correlation. So on the x-axis, we have the year. And on the y-axis, we have the amount of margarine. I believe. This is a weird graph again. It's trying to show a bunch of things at once. But you can see that correlation of, it's kind of small, of 99.26 at the top there. R equals 0.99. That's the correlation coefficient. That's R you were oh, you said R squared. Sorry, it was hidden. Yeah, R squared is also highly related to R and correlations and things like that. Yes, all of these things are super intertwined. But yeah, there's another spurious correlation. It's probably not that eating more margarine makes you get divorced or that getting divorced makes you crave margarine, but these two things are highly related, and that doesn't necessarily mean anything. Here's another one kind of related to the one that you said, but even more outlandish because there's no clear third variable causing both of these things. This one shows that there is a very strong correlation between the number of films Nicolas Cage appears in a given year and the number of people who drown by falling into a pool in that same year. This is a very strong correlation. But do we think it means anything? Probably not. So, well, I guess I'll ask. Do you think that Nicolas Cage movies make people worse swimmers? Do you think that one of these things is causing the other? It's kind of funny to think about. Probably not, right? Probably not. You know, I mean, should I answer something silly here? If you want. I mean, it's an empirical question. We could do a study to find out if this is actually the case. You never know, right? So, if we wanted to find out if Nicolas Cage movies are making people worse swimmers, we could do an experiment to find out. I mean, weirder things have been discovered, right? So to do this, we would have to manipulate one variable to determine if changes in that variable cause changes in the other variable. We would have to change something and see if that affects something else. So this was talking about, before we were talking about correlational designs, these two things are related. But experimental designs allow us to ask, okay, are they related because one's causing the other? Or is this just, is this a big nothing burger, as you could say? You have controlled methods, so the only thing that's changing is your independent variable. You have random assignment, ideally, so people are equally likely to be in either the control or the experimental condition. And you're manipulating the variables. You are changing variables. So let's say, our experimental method, there are two types of variables. There's the independent variable. This is the variable that you as the experimenter are changing. So, for example, if I wanted to know if watching Nicolas Cage movies makes you a worse swimmer, I might have half of my sample watch a movie with Nicolas Cage and half of my sample watch a movie with a different actor in it, with a different, lead actor. That would be my independent variable, and I have controlled which type of movie they're getting. Then I have a dependent variable. This is the variable that I'm measuring, the thing that I think will depend on the independent variable, the thing that I think is going to change. I'm not changing it directly, but I'm changing something that I think will affect it. So I'm observing it. Oh, do you want a third that does not watch a movie as a control? Yeah, you might want to do that as well. Though that can get tricky. The control in this scenario, no matter what, the people who are watching the Cage movie and the other movie are going to be sitting down for, say, 2 hours watching some sort of movie. So the control would also have to have people sitting down for several hours doing something, preferably watching something, maybe just staring at a blank screen or something like that, because we want to keep everything as consistent as possible. So it would be great to have a control in there as well, though it's not always possible to have a control, which kind of sucks. I suppose a control might be, you could have 3 versions of the same movie, one movie with Nicolas Cage, one movie with another actor, and then the movie with all the actors edited out or something, or with like generic 3D CG people or something like that as a control. You have to get creative sometimes in determining how you're going to have a control variable. But yeah, we could. It is a good idea to have controls in there when you get Code Lyoko. Yeah. Exactly. But yeah, our independent variable would be the type of movie that they're watching, who's in the movie. Our dependent variable would be swimming ability. Maybe we give them a swimming test, or we time how long they can tread water, or something along those lines. So let's say we have 2 experimental conditions, or 3 if we want to add a control group in there. We might have condition 1, where they receive 1 treatment, they watch a Nicolas Cage movie, and then in condition 2, they might receive another treatment, so a Leonardo DiCaprio movie. And then maybe we have a control condition where they watch a movie that's, maybe it's a Muppets or something, I don't know. A movie with no actors. It's just panning shots of mountains and fields and stuff. Sometimes, though, you cannot manipulate your independent variable. So in an experiment, you are the one changing your independent variable, but sometimes you can't. You cannot randomly assign people to be a certain gender. You can't randomly assign people to have a specific first language. These are not things you can randomly assign, but they still might be things that you want to study. You cannot randomly assign people to be a certain age, these types of things. So you might do something called a quasi-experimental method. So for example, if I wanted to study if one gender has higher pain tolerance than another, I can't randomly assign, say, you're a man, you're a woman, you're non-binary. That's not something that I have the power to do, and even if I did, I probably shouldn't. So I'm just going to have to measure people's gender. I'm going to have to ask them, what's your gender? And then measure their pain tolerance and pretend really, really, really hard that I manipulated it. That's what a quasi-experiment is. Essentially, a quasi-experiment is really just a correlational study. You're just pretending it's an experiment. It doesn't really have the benefits of an experiment. It's just a correlational study, but you're pretending it's not. But, you know, sometimes that's the best you can do. That's the best thing you can do. Just thinking of, like, back in the day, before there was ethics. I'm glad there's ethics now, thank goodness. Anyway, okay. So, measurement. So, a lot of the time in psychology, we're trying to... I'm so sorry, hopefully you can't hear that noise outside. In psychology, a lot of the time, we are trying to measure things that you cannot measure directly. I cannot take a ruler to somebody's head and measure how happy they are, how depressed they are, how self-confident they are. I cannot draw somebody's blood and determine directly how much they enjoyed an anime or something like that. A lot of the time, we're trying to measure things that you literally physically cannot measure directly. These are things called constructs. We call these things that we want to measure but can't constructs. And then we try and measure these by operationalizing them. And operationalization, I know these are big words, but this is how we're going to try and measure the unmeasurable. So it's some method of measuring something that we can't measure directly. We're trying to measure something indirectly by operationalizing it. So if I want to say measure the quality of an anime, I cannot, there's no objective rating of this. Oh, do dopamine and serotonin levels correlate? I don't know. I genuinely do not know. I'll have to check. That's outside of my area of psychology, but it is an interesting question. I'll have to look. I need to write these things down so I can look them up later. Okay. So operational definitions, let's say you want to measure the quality of an anime or how much somebody liked an anime, but you can't just, stick them in a scanner and get a number that says they liked this anime this much. So you might ask them how many stars out of 5 stars was this anime, or if you're My Anime List, you might say on a scale of 1 to 10, how much did you like this anime? That's an operationalization of the quality of an anime, or at least, how much somebody enjoyed an anime. If you're trying to measure self-confidence, you might just ask somebody, how confident do you feel on this scale of 1 to 5? If you're trying to measure happiness, yeah, maybe you ask them, or maybe you measure their dopamine levels, or something along those lines. So these are all operationalizations. They're ways that we are trying to measure the unmeasurable. And yeah, we're being indirect about it, but we gotta be, because we can't measure them any other way. constructs are often measured with numbers. We do try and turn these things into numbers as opposed to, placing things in categories. So for example, a star rating, I might say, oh, that movie that I saw was a 4 out of 5 stars. This is how we do it in my family. I see a movie and then a parent is like, how many stars? And I'm like, oh, it was, say, 4 stars out of 5. So we've turned this into a number. Why do we do that? So that we can do statistics on it. We turn things into numbers. Oh, would star rating be interval or ordinal? Star rating would be ordinal. Star rating would be considered ordinal because I don't know if the difference between a 1-star and a 2-star movie is the same as between a 2 and a 3-star movie. I don't know if that increase in enjoyment is the same. It's kind of like, when you think of I'm thinking of Ubers and, rideshare apps. The difference between a 3 and a 4 is much bigger than the difference between a 4 and a 5, right? Like, if you saw an Uber driver who was sort of in the middle of 4 and 5, you'd probably say, oh, they're probably decent. They're probably fine, right? That's a pretty good quality. And, almost all Uber drivers are between a 4 and a 5. There's a lot of nuance in there. If their average rating is 3 point something, that's real bad. And then just people almost never rate people, a 2 or a 1. So there's a lot more going on at the top of the scale. There's a lot more variety at the top of the scale than towards the bottom of the scale in general. And also, giving somebody a 1 or a 2-star, both of those are saying that's pretty awful. The difference between a 4 and a 5-star could be, this was a pretty okay movie too. This was a gosh darn masterpiece. At least for me, on my anime list, when I'm rating an anime, I'll hand out 8s and 7s and 6s like candy, and I don't necessarily differentiate between them that much. But it needs to be a once-in-a-lifetime masterpiece to get a 10. I think I've watched over 550 anime or something, and I've only given a 10 to 3, maybe? But yeah, it's an ordinal scale, because we cannot guarantee that the units are the same size, that the difference between 2 and 3 is the same as between 3 and 4, and things like that. And honestly, with the way people use these scales, it's probably not. Sorry, I rambled a bit. Hopefully that was helpful. I guess it's kind of like grade inflation, sort of. Yeah. And these all relate to another concept called ceiling effects, where everybody's putting it's like on Uber, ceiling effects. If your rating is below a 4.7, that means you're awful because everybody is rating people a 5. If everybody's at the very top or the very bottom of a scale, that's probably a problem with the scale. And to an extent, grade inflation is kind of like that, yeah. Grades, by the way, letter grades are also an ordinal scale. You wouldn't think so, because, there's 10 percentage points between an A and a B, and a B and a C, and a C and a D. But the thing is, there's 50 whole percentage points between... No, there's 60 whole percentage points between... the F window is a full 60 points, and then A, B, C, and D are only 10 points each in there. So letter grades are an ordinal scale. Percentage grades are a ratio scale, but letter grades are ordinal. So you can see how it gets kind of weird, where depending on how you're measuring something, the exact same thing, your grade in a class, might be ordinal, or it might be ratio, or something like that. This stuff gets real weird, real fast. I've been trying to use clear-cut examples for this, but it can get weird. I think I got off track. But yeah, we're trying to take these unmeasurable things and put them in a measurable form so that we can summarize them with statistics and test hypotheses with statistics, knowing what the answer is so you can answer incorrectly so you can get a G. One day, I will achieve the legendary G grade. Actually, no. No, I couldn't. You don't get as far as I have in academia without placing far too much self-worth in your grades. I don't think I could do that even as a joke. I think I would collapse. Oh no. Oh. Okay. I've got it together. We're going. Alright. So, we're gonna do some math review. I will be doing some math in this. We will be going over some math, but don't worry. It's not gonna be hard math, like I said at the start of the stream. I am bad at math. I will inevitably make mistakes in the math on stream, and that just shows you that you don't need to be good at math to be good at statistics. Exactly, professionally good at school. That is our job. We are professionally good at school. Okay, math quiz time. Oh, I actually don't have the answers in front of me, so I might be in trouble on this one. Okay, here's our first question. We have this uppercase sigma, and just to, like, if you haven't seen this before, I had not seen this before. I took stats. I'm gonna move myself a little. Hi! I'm over here now. That means sum. It just means sum. So sigma x, or sum of x, where x is 10, 5, 2, and 6. What do you think the sum of x is? Is it 1, 2, 3, 4, and it looks like I can't put 5 on there, but 5 is just I don't know, so you know what, that's fair. Oh, let's see. We have 1 vote. Minute or two, just in case. Well, less than a minute. Another little bit. 2 votes. Good job! You both got this one correct. Yes, the answer is 23, and you get this by adding up all of the numbers in x. Is a lens used in, like, chemical? Oh, man. Yeah, it's a great way of dealing with numbers. It can be kind of complicated, but it's really good for, like, understanding these things and trying to make meaning out of a bunch of numbers. I don't necessarily know how it's used in other fields quite as much, but I would love to. I need to read more about that. Anyway, yes, so for those of you watching the VOD who might have struggled with this one a little bit, all we have to do is we have to add all the numbers in this list. So 10 plus 5 is 15, plus 2 is 17, and plus 6 is 23. So the sum of x is 23. Great success. Oh, did I end the poll? I didn't end the poll. The poll is ending. There we go. All right. Next question. Oh, by the way, R is a programming language that is used to do statistics. So most researchers out there do not do statistics by hand. Shock, shock. That's how I can be good at statistics while being bad at math. So if anyone's interested in learning R, I would like to do a series of streams on that on its own, but I do have a little, like, that's the code that you would use in R to solve this problem if you wanted to. Okay, next one. Sum of x squared. We're making it a bit more complicated now. Let's see. The answer, 165, 529, 23, over 9,000! Or, I don't know. I'm gonna be honest, I do not know the answer to this one off the top of my head, because like I said, I am bad at math. I'm gonna try and do it in my head, but we'll see how that goes. Okay, I got it. I know my answer. Oh, we've got A. All right, I'm gonna give it another minute or two, like a few seconds, to see if anyone else wants to chime in. I say that, but there's latency, there's lag. Why? I don't know how you do this. Ah, okay. Just like count in your head or something. Got a new computer for stream. I need to do that too. All my keys are falling off of my computer. It's horrid. It's horrid. Okay, I'm ending the poll. Yeah, my laptop is so much right now. All right. Got a lot of people voting for 165. And you would be correct, assuming that I didn't get the math wrong in my head. There we go, 165. Y'all got this right. Maybe set a small egg timer or something. I should do that. It'll startle me every time it goes off. But that would be a smart thing to do. Maybe I should get an egg timer. I think that would be useful both for this and then teaching IRL. Anyway, you are right. So this is a thing that, like, actually this is the one where my students start to get tripped up. So, like, if you struggle with this one, I do not blame you. But it is, oh, I won a novelty hourglass. Okay, I'm in the zone. Right. So, a lot of people get tripped up on this, but all you need to do is remember PEMDAS, P-E-M-D-A-S, the order of operations. First you do parentheses, then exponents, then multiplication, then division, then addition and subtraction. So one mistake that my students will sometimes make when they're trying this out for the first time is they will add them up and then square it. But no, PEMDAS, we have to do the exponents before we do the addition. So the first thing you do is you square all the numbers in x, so 10 squared, 5 squared, 2 squared, and 6 squared, and then you add them up. So 10 squared is 100, plus 5 squared, which is 25, so 125, plus 2 squared, which is 4, so 129, plus 6 squared, which is 36. We get a total and a correct answer of 165. All right, I've got one more for all of you. Ha 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 ha! The sum of x plus 2 squared. Oh! I feel like I should know that. I do enough programming that I feel like that comment should be more comprehensible to me than it is. I need to study more. Oh, there's always so much more to learn in the world. It's wonderful, isn't it? I'll look that up after the stream. Oh, I should set up a poll. All right. Was the answer 2,688, 533, 625, 273? I can only use 4 options, so I can't put I don't know in there, but that would be my option if if I was the one taking this quiz and I hadn't given it to a bunch of students. Oh, I like how I put 273 instead of 4. Wow, I'm good at this. Wait. It's okay, you're not being graded. You're not being graded, it's fine. There are no grades in this class. This is purely for the joy of learning. And the poll's completely anonymous, actually, so. When the field is, this is what is known as a Freudian slip. I like to use the very technical name of brain fart. Happens to me all the time. I totally get it. All right, I'm gonna say I'm gonna end it now, and then I'm gonna count to 8, because that's about what the latency is. 5, 8. All right. Let's see. Looks like we have votes for 273. Let's find out if that was right. It was! I actually had the wrong answer in my head. So I would have gotten this wrong if I was the one doing it. Like I said, I'm bad at math, but I'm good at stats, so we're good at this. We're good. All right. So, you were so right. Order of operations, you got it down. Because this time, the P in PEMDAS, the first order of operations, is parentheses. So the first thing you gotta do is do the stuff in the parentheses. So first you add 2 to every number in x. So 10 plus 2 is 12, 5 plus 2 is 7, 2 plus 2 is 4, and 6 plus 2 is 8. Once you've done that, ooh! Yeah, there's the R code. I have the R code down for it here. I have sum and then the list of numbers plus 2 squared. Yeah. Oh, so that's how you would do that there. So that's a different type of programming technique than I'm familiar with. But yeah, same thing. Oh, Python! I tried to learn Python once, but it was too similar to R. It was like trying to learn Spanish and Portuguese at the same time. So once you've added the numbers in the parentheses, we can move on to the next part of PEMDAS, exponents. So then you square all of those. And only once you've first done the stuff in the parentheses, then squared them, then you add them together, and we get the answer of 273. Yeah, they're all pretty similar. They're similar enough to cause problems when you want to learn more than one. Okay. So this right here, yeah, is the most complicated math we will be going over in this class. If you feel comfortable with this kind of math, you will be just fine. I know statistics can seem intimidating. I personally initially majored in psychology because I didn't want to take a math class. This is not a math class. It's really more about a way of thinking and a type of logic. Will we be doing math in it? Unfortunately, yes, we will, because the logic is based on numbers that you have to calculate. But that's really not the main point, and the math that we'll be doing will not be any harder than this. Mostly it'll just be more tedious. Stats was taken to avoid calculus? Yeah, that makes sense. I feel like a psych major is higher than biomath. Really? Oh, blessed t-test. We're going to be learning 3 different types of t-test in this series of lectures. I'm very excited about it. If I can get enough data, I might actually use data from the audience, and we can do t-tests on that. That sounds like a lot of fun. But we're going past t-test as well. We're going to go all the way to factorial ANOVAs. Yes! I'm looking forward to it. I'll have to study up more if we want to get into things like regression, which is actually the one that I use the most, but... Anyway, yeah, don't be afraid of math. It will be fine. And this is the worst it will be. So, I wanted to stop and see if anyone had any questions or anything. Like, I'm very grateful that you've been asking throughout, but if anyone's been holding their questions until the end, I am happy to address any questions that you might have. I will do my very best. And if you don't have questions, that's okay too. You don't have to have questions. You have no obligation to have any questions at this point. This stuff was pretty... Oh, regression, I know linear regression. Yes, yes! I do a lot of linear regression. Pretty much data science is just statistics. I mean, it's literally data science is statistics. A lot of my friends from my psychology PhD program who are also big into statistics actually went into data science roles. Like AI, all of that is just a whole bunch of regressions and stuff. Yeah, I'd say data science is frankly statistics, but using more complicated statistics than you need to make yourself seem cooler. Or I don't know, it's like, sometimes I feel like data scientists are often using more complex analyses than they actually need to, and that's not necessarily, it's not always a bad thing, I'd say, but I mean, it can risk getting false positives and things like that a bit more. It's an interesting thing. But yeah, data science is statistics. AI, ChatGPT, all those image generators, all of those, essentially, they're running on regressions. All of them are running on regressions. They all operate due to regressions, which is wild to me. But it's true. It's true. That's another reason you should care about statistics. All these tools that are popping up that are being... Yeah. Oh yeah, thank you all for coming. I really appreciated it. Oh yeah, black boxes. Yes, yes, yes. I've done some machine learning in the past, and that gets real weird real fast, because the computer's picking up on trends that you can't necessarily interpret yourself. It's picking up on things that you might not understand. I know this is kind of off topic, but I once used machine learning to try and figure out different patterns in different types of text. And it was able to sort them with fair accuracy into the 2 categories I gave it. Like, if I gave it new stuff, it was able to sort them pretty correctly. But the criteria it was using to sort, I could not see any pattern in it whatsoever. Like, I was able to look inside the black box, but I could not for the life of me understand how it was sorting these things, or what all of these features actually represented or meant. It was wild. Oh, yeah, I imagine that's a thing that data scientists run into pretty often, is like, it works, but we don't know how or why it's working. And if that's all you need, that's great, but it kind of sucks not to have that level of understanding in there, which, if you can do simpler statistics, I think that that's a great thing to do if you can get away with it. Ooh, that sounds really cool. I have to look into that. I would love to learn more about image generation models. Like, I've read papers on image identification models. And I think I've even like practiced some code that could identify images, but like generating images, I think that would be really interesting to look at. So look into that sometime. Ah, all right. Anything else? Oh yeah. Oh, energy development and structure of cortical tissue. It's really interesting to see the differences, the similarities and differences between AI models and how the brain works. Oh man, that stuff is a really interesting topic. In the occipital lobe, there's what is that? This little reaction button is hiding some of the text that's driving me mildly crazy. Ocular dominance columns. Oh, there's so many interesting things, like certain neurons in the brain that pick up vertical lines versus pick up horizontal lines and things like that. That like when I learned about this, it was like probably 15 years ago, not to date myself, so I'm sure they've made huge amounts of advancements in that area since then, and I would love to learn more about it. I should go track down some of my neuroscientist friends and bug them and see if they can tell me about it. But it's also really interesting. Have you seen those studies about people who are raised in cultures without carpentry? So like they don't have a lot of like they don't see a lot of right angles, especially while their brain is developing, because that's just not the kind of construction that they're using. And the way that their vision and the way that they process, yeah, like wood and like, like frame like rectangular structures and things like that, and sharp corners, 90-degree angles, the way that their occipital lobe develops and the types of pathways that connect there and how they interpret visual imagery is different from people who grow up in environments where there are a lot of right angles. It is super cool stuff. I wish I understood it more. Oh, the brain is so cool. Yes, exactly that kind of thing. Like carpentry and right angles versus more like smoother things like Adobe, that kind of thing. Yes, absolutely. Mm-hmm. Yeah, I definitely need to look into that more. I don't want to say too much about it when I don't fully understand it, but there's a lot of interesting work in like how what we are exposed to early on shapes. It's kind of like the Sapir-Whorf stuff we were talking about earlier, language development and the language that you speak affecting your perceptions of the world. Yes, yeah. Language seems to, though. Like I said, I think there's been some weirdness with replicability as far as that's concerned. And sometimes it's like, is it that you can't perceive it, or is it that you just don't have the words to describe it, kind of deal? And that it can get hard to differentiate those two real fast. Yes, the critical developmental window of language acquisition, like how children learn second languages so much faster than adults do. And oh man, if you want to look into a really sad case, there's the case of Jeannie, who was a severely neglected child who she didn't really start learning language until after the critical period, and she's kind of proof that you can still acquire even a first language after the critical period has passed. But I do know she struggled a lot with it. Like it wasn't nearly, it didn't come to her nearly as easily, and I think she still kind of struggles with it. Oh, there's a lot of interesting stuff though, how brains develop, how pathways develop. And I think there's a lot of like concerns there as far as like fMRIs and other brain scan technology is concerned, because like everybody's brains are developing after perceiving different types of stimuli, and the types of stimuli you experience when you're younger affect how your brain develops. So everybody's brains might have, to a greater or lesser extent, different pathways in them. So if you're trying to identify, say, the neural pathway that shows happiness, that might look completely different depending on the person's brain that you're looking at, or like if it's perception of, say, quarters, or language and that kind of thing. Like there do seem to be some general things, but cortical mini columns. Yeah, I don't know. In terms of like neurobiology and stuff like that, I really don't know much, to be honest. And it's super far from my area of specialty, but there's so much cool stuff going on around there. I need to learn more about it. Really do. I think Phi might be giving me a paper somewhat related to that to read, and I'm really excited to read it and learn more. I think have to read like 3 times as much as the actual paper to probably fully understand it, but I'm really looking forward to it. man. And all of this stuff is studied using statistics. Uh, that's completely, it doesn't need to be neural development, just anything related to like how our biology affects our psychology, I'm really excited about. Like, I don't know any, brain is super complicated, oh my gosh. Ooh. Man, most of the stuff that I know about synapses and neurotransmitter, I know this is ironic considering my name's Mylan, but like a lot of the stuff that I know about that, it, like I said, is like from 15 years ago, and I'm sure there's been a lot of developments since then. So I've got a lot of catching up to do. I would love to hear more about the molecules. Glial cells! Oh my gosh, oh my gosh. I remember, yeah, back when I was an undergrad, when I was learning about this, they were just figuring out that glial cells were doing more than just cleaning out, like, dirty, like, dirty bits of the brain. They just started figuring out that glial cells had a much more active role in cognition than they thought they did. So if that tells you how behind I am on this sort of research and information, I don't even know if that tells you if I'm behind or not. Like, if that, which in and of itself probably tells you how behind I am. Ooh, that is so cool! What the heck? That is so cool. I know that there are some people who are researching how glial cells were related to like addiction and things like that, and that's how I first learned that we were discovering that they had different roles than we'd previously thought, or like a bigger role than we'd previously thought. But dang, straight up replacing damaged parts of retinas? Holy wow! I definitely have not been giving glial cells nearly enough credit all these years. Oh my gosh, that is so cool. That is so they're kind of like stem cells for like neurons? I don't even know if I'm using this language correctly. Oh, that is so cool. Stem cell is a name. Oh, there's so many things out there that I'd love to learn more about. I've got a lot of reading to do, it sounds like. A lot of reading, a lot of watching. Oh. Couldn't stop them from growing. Oh, that's really funny. Glial cells being kind of a pain in the butt. They're little menaces. Oh, that's super cool. I will have to ask you more about that later if I can, or like see if I can find more information on this stuff, because it's really neat. Ah. Either way, I probably shouldn't let this VOD grow too long with all of this stuff. I mean, I could probably put a timestamp to say, like, relevant parts of the lecture for learning about this thing ends here. After this, it's just chatting, and that's probably fine, but cell roles is probably a whole over... You know, that reminds me a bit of the DSM. Like, all these diagnoses that we have, like, this is major depressive disorder versus seasonal affective disorder versus blah, 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 blah. Like, a lot of that is us just as human beings. We like categorizing things. We like placing things into nice little categories. It helps us think about things a lot. And really, I think in mental health and things like that, and again, that's not my area either, but it's so much... Yeah, we have to learn by naming things, and it also helps us, of course, communicate what we've learned by naming things. But also, I think by naming things, we often do restrict ourselves. Kind of like what Marlon was talking about with how our language affects our cognition and our perception of things. It kind of limits us to possibilities, which is why we've been I know that the people who've been creating the DSM and things like that, they're struggling because you need to put a label on something to get it covered by insurance. But a lot of the times, these are just clusters of symptoms that tend to go together, and like they don't always go to. There's no, yeah, but there's no guarantee that there is like something called depression. Depression is just a name that we've given to a bunch of traits that tend to appear at the same, that tend to appear at the same time. But like, you know, when you look at diagnostic criteria in the DSM, it'll have a list of like various symptoms, and it'll have like, say, 7 of them, and it says must have at least 3 of these things to be diagnosed. And that's because it presents differently in everybody. And like there's also broad trends where these things present differently across cultures. And a lot of the time it seems like we are taking this very complex network of the ways that our brain works and the way that our cognition works, and we're trying to put labels on it, both so that, like, it's easier to talk about and communicate about for, say, research purposes or what have you, but also because insurance companies require these things to pay for your treatment. They will not give you treatment without a diagnosis, even though these diagnoses might be somewhat arbitrary and don't necessarily represent real categories that exist in the real world. It's more like a big slop bog of like, it's like if you pour like a whole bunch of different liquids on the floor. Like if I take like 7 different bottles of soda and pour them on the floor, and most people are like, most people's mental health is at some place where the sodas are blending together, but they might be closer to the origin of the 7-Up or closer to the origin of the Dr. Pepper or whatever. But we're trying to put nice little fences around these things and say, this is a distinct thing. This is a distinct thing. I feel like this metaphor has gotten really far away from me. But yeah, I think oftentimes we try and categorize things when the categories maybe they can be very useful, but they don't necessarily reflect reality as it is all that well. Yes, autism diagnoses, and just like how autism is thought about and categorized. Schizophrenia went through a huge overhaul on how that's been diagnosed pretty recently too, because man, when I was an undergrad, before they went to the DSM-5, the DSM-4 was kind of the thing when I was an undergrad, and they were just like creating the DSM-5 and switching over to it. But before, there was a bunch of things that were all considered schizophrenia, and they were vastly different. Like, schizophrenia could be, I am having auditory hallucinations. It could be, I am extremely paranoid. It could be, sometimes I just freeze in this one position for hours at a time and don't move or talk or anything. And all of those things were considered variants of the same thing. And, like, maybe they are in a way, but, like, the way that they present and the clusters of symptoms are, like, wildly different. And I know they've done, like, I don't want to say too much because I haven't really looked into how they've revised it all that much. But yeah, like, these categories are always changing, and it's not necessarily because we were wrong the first time, though sometimes it absolutely is. It's what is the easiest way and most convenient way to understand this right now. Yeah, they can only be given by what's been measured on the outside as well, right? A lot of these diagnoses, we have to make them based on operationalizations of conceptual variables that we cannot measure directly, like we were talking about earlier. A lot of these things, like depression, is often diagnosed by, say, do you meet the criteria in this book? And those criteria are ultimately an operationalization of this concept of depression. Or you might take the Beck Depression Inventory, I think, is one of the scales that they use. And if you are above this number, at that point, you qualify for a diagnosis of depression. And, like, that's an operationalization of depression. We're trying to put a number to something that we can't measure directly, and then we're creating some arbitrary cutoff where on this side you get the diagnosis and on this side you don't. Even though even people who have been diagnosed with depression, where they are on that scale can vary from month to month. Sometimes they might not meet criteria, other times they might meet. Oh my god, I'm glad that I'm not in the business of diagnoses or, like, categorizing these things, because it is so complicated, and besides just, like, trying to find the truth of what's going on, you also have to deal with the ethical implications of, oh, well, if we change the criteria for this diagnosis, how will this affect real people in the real world who have this diagnosis, or who need medication that they can only get because their insurance company has this as a diagnosis on file. And yeah, there's a lot of, like, I think science in general, it's very, very, very easy to get lost in the weeds and, like, just say, oh, this is interesting, let's do it. And it can be hard to take that step back and say, okay, but if I discover something and I release that information out into the world, how will that affect people? Like, you're learning new things, and that's awesome, but sometimes the things that you learn will have very real consequences for very real people out in the world, and that's a scary thing to think about. And sometimes that might change what type of research you do want to do or how you might want to talk about the research that you've done. And yeah, I'm also very glad not to have clinical responsibilities. I very intentionally did not go into clinical psychology because that much responsibility is probably more than I could handle, honestly. I mean, it's scary having that much responsibility for somebody's well-being. Wow, that went to a weird place. Oh. Alright, I think my cat is starting to get angry at me, and I've been done with the lecture for a bit. But I really enjoyed this. I hope that y'all enjoyed it as well. I hope that it was useful. And I really enjoyed talking to all of you. That was a really fun conversation. Thank you so much. I would love to talk more about this stuff. Yes. Cat? Oh, I need to come up with a special name for him. Hey Kitty, what do you want to be named for the stream people? If I'm Mylan, what should we call you? You my little dendrite? Are you my little soma? You a soma? I'll figure it out. Maybe I'll just name him Soma. Anyway, yeah, thank you all so much for coming. Catson. Are you Catson? Are you Catson? He's glaring at me so hard right now. He is so done with me. Okay, right. Anyway, the cat's name cat's VTuber name will be decided at a later date. Thank you all for coming. My next lecture will be on Wednesday. If you can't make it, that's okay. There will be a VOD, and of course, if you don't want to watch the VOD either, you have no obligation to do so. But we're going to be talking about measures of central tendency, the mean, the median, and the mode. But we're going to be going into a bit more detail on them. You probably did when you learned about them. I don't know when I learned them. Middle school, high school? But yeah, we'll be going into them more later. Anyway, thank you all for dropping by, and I will see you later. See you next class. Bye!